continue looking at it and saying that this primary position, if I showed you this in 118A, you would say that doesn't make sense. Right? 118A, we said that in order for you to go SN1, we need to be secondary or tertiary. But this primary position, because it's next door to a double bond, actually operates SN1. So this will be a little bit review from substitution elimination that we learned about in Ed. At this point, what's going to happen if we're going SN1? What we're having next?
Carbocation.
Okay, carbocation, and then? Do I have a nucleophile, or what would be my nucleophile here?
CO.
My methanol, right? So I can draw my methanol being added, carbocation, I'd deprotonate, and I'd end up with my product here. And so we actually will see this operating via SN1 simply because there is a double bond next door. What I'd like you to think about for most of today is if I showed you this Lewis structure, could everyone draw me the resonance form for that? Right? Push arrow down, push up, and we'd say that this would be my resonance structure, right? Remember doing that? That's all we're working on today, except we're doing it with carbons. So what that means is when we have this free radical generated, this radical is not stuck on this primary position. It gets some help from the double bond. This carbocation that forms is not stuck on that position. It gets some help from the double bond. And in fact, we can see this even with anions. So the pKa of a normal sp3 carbon is about 50. This, about 40. So what we're saying is that all the chemistry we've learned gets a little bit easier when you're doing it at an allylic position, next door to a double bond. And so all of these observations, right, we've done free radicals before. We've talked about acids and bases. We've talked about SN1. Now we're learning, oh, wait, let's not talk about the double bond, right? Think about why we started. We started with alkenes, reactions of alkenes, alkynes. Now let's go back to something that has an alkene in it. But chemistry is going to happen at a different spot. So, again, I have up here, just to make sure we're clear, the allylic position, the carbon next door. And this doesn't mean I only have one allylic position, unless it's a terminal double bond, right? I could have two, on the left and the right. All of the chemistry for this chapter is going to be based on this allylic position. So what that means is I could draw resonance structures for all three of those processes I just talked about. Free radicals, anions, and carbocations. And I want to point out differences with the arrows, right? And so I want you to give me the structure that's missing here and draw the arrows to get back to this one. That's what I'm going to ask you to do in a second. But let's review. For free radicals, we know we need the half hook arrows. So I don't want to see any double arrows for this top one. For the bottom one, I don't want to see any arrows starting at positive charges. Right? We're showing electrons moving. There's no electrons at a positive position. And for the last one, these arrows are the newest ones because we haven't focused so much on moving negative charges. But I want to point out the small difference with these. Notice I'm putting the negative charge and pushing it towards the bond versus pushing the bond towards the carbon. Those mean two distinctly different things. And that's why when you started drawing substitution elimination reactions, it was really important for you to show, are you making a new bond or are you strengthening one? This arrow, by pushing electrons to this carbon, what is that placing on this carbon on the end? An extra lone pair, meaning a negative charge. Okay? So I want you to get some practice, see if you can draw the resulting picture of the arrows I've drawn here, and then draw me the arrows to get back. Okay? Don't worry about the OR just yet. OR is going to be essentially our resonance hybrid, right? A combination of both of those pictures. And so if the arrows are tough, that's why I've included the arrows on your sheet already. I want you to draw the other one and then add arrows to go back. So this is just an exercise in reviewing arrow pushing.
Brandon?
Yeah.
Is it a bad habit that I want to like switch these to bond line before I do anything?
No, that's fine.
Okay.
That's totally fine.
So I should get used to this.
Yeah, no. So I'm using figures from the book, and they always like to show each individual carbon.
Mm-hmm.
And I do think it's helpful when we're moving around electrons, negative charges, or positive. But to be honest with you, as you saw in the exam, you're really going to see bond line moving forward. So I think that's totally fine.
Okay.
Those are good structures now. Arrows to go back here. Great. Okay. Quick refresher with this, because this is where I usually find if you had trouble with substitution or it's been a while since you took CHE118B, some of these little intricacies might be forgotten. So if I'm asking for resonance, I have 3 arrows here. I better see 3 arrows in the resulting product, right? Let's first focus on what this is showing. Free radical, I'm taking this extra electron and I'm taking 1 electron from this carbon. Those are meeting together, so that means that there's going to be an additional bond there. That means that this electron is being placed on this carbon, so my radical will now be on the carbon on the left. And in order to get back, I'm going to reverse this process, putting these 2 electrons together and placing that one on the end carbon there. So what we can also think of this as is that there's not a free radical on this carbon on the left. There's not a free radical on the carbon on the right. There's a radical that's spread out amongst those 3 carbons. All right? And for the radical part, I'm going to say we're not going to focus so much on that. We'll do the first reaction today that will use that. But for the most part, where I think delocalization is important is this next one. Because we know when we see a carbocation, we're going to add something to that position. But if I'm having delocalization, I don't have a carbocation only on this carbon. I also have it on this one. And so everything we've learned with carbocations, what is that going to mean for the types of products we're going to see for these? We can always have 2. I don't have a carbocation only on one of these carbons. And in this case, it's symmetrical, not going to matter. But you know I'm going to give you one where it's not symmetrical, and that adding that nucleophile to the carbocation on the left is going to give you a different product than when you add it to the one on the right. Even though we haven't seen much about carb anions, they do have the same arrows. I do hate to be a stickler for this part, but it really is important to make sure this arrow was to the bond, this arrow was to the carbon. Right? I don't want you drawing it to the hydrogen, showing a double bond with the hydrogen. I don't want this pointing to this carbon. Okay? Just to be clear with how you're drawing and where those arrows should be pointing to. Okay? And the same thing, we can have sort of a hybrid where we're saying that negative charge is not carbon, it's actually moved between all 3 of them. And I've added them for you, but this is the advantage of this allylic system. I can have all these p orbitals overlapping, and so they're all sort of going through the same thing together. when we add a problem to it, when we add a radical to it, when we add an anion to it, they're all saying, what can we do to help each other? And carbon does this a lot. We're going to focus on that more in the benzene chapter, right? Being able to say carbon is something that's electron donating. It helps other carbons out, right? That's why a tertiary carbon is a better carbocation than a secondary. Carbon's there for support, right? That concept of hyperconjugation. You guys remember that buzzword from 118A, right? That sort of sigma bond hugging that it's doing to that positive charge. That's really what allylic systems are all about. So, if we're showing how this mechanism is going to happen, my first step will be generating this primary carbocation, right? I can now kick off this bromine because of the support of that double bond on the left. So, what would my two carbocations look like? I know I'd have one with my carbocation on the right. And I don't have the arrows here, but you should be able to draw them, and how that carbocation would get to the position on the left. I still would have my bromine, right? We need to have mass balance. That bromine didn't disappear. And so if we're saying we're generating this carbocation, well, this doesn't really fit into our system, right? We always said tertiary is better than secondary, is better than primary. But this is a primary, but it's not really. And so we sort of have to change the way we're ranking our carbocations from now on. We're going to say that since this positive charge is delocalized, even though it's delocalized over two primary positions, it's going to be better than a primary. If there are carbons that are more substituted, right? So think about this. I'm going to be pushing this double bond over. This is now a secondary carbocation. And if I use the double bond to push over, I have a combination between a secondary and a primary. Well, how do I know if I'm thinking about stability? How do I know which one's going to be better? So our new ranking system is going to be our primary is going to stay the worst. Or sorry, methyl is going to stay the worst, then primary. Now we're going to say secondary with an allylic position being about the same. And if it's a substituted allylic, it's going to essentially be about a tertiary. Meaning that when I see a positive charge split between two primary carbons, it's essentially as good as a secondary. And so that's the reason why when we're allylic, we can have SN1 happening. So this is the big takeaway from this part. Don't treat allylic primary positions as primary carbocations. You can still go SN1.
So I learned that without the allylic system, that primary doesn't even exist, primary carbocation. Is that just what we're taught at this level?
Exactly. So
it does exist, but it's not at
it can happen rarely, but again, it'll always rearrange, right? So there are times where if you have a primary and a tertiary, you will see that change happen right away.
Yeah.
But you're not at the point. That's more of a question where it's, hey, how did I get this product? Show me, as opposed to predict this primary carbocation shift. Okay. So I would say, moving forward, you're saying a primary shouldn't be made unless it's an allylic.
Yeah.
Okay. And it's because of this new ranking system that you're seeing a primary allylic position as good as a secondary versus a substituted allylic being about a tertiary. So here would be my summary of everything, right? This is what you're imagining. If you want to keep your normal system, tertiary is the best, secondary, primary, treat these as approximately about the same. We go up one level because we're essentially splitting it between two. Two carbons have half a positive charge, like a secondary. If it's substituted, it's like 3 carbons have a positive charge, or a secondary and a primary have it, it's like a tertiary. Okay? So just to give you some easy practice, what I want you to do is, if I have 3-bromo-but-1-ene, what would the carbocation be? Is there a resonance structure of it? And you shouldn't need it, but that's what that looks like, right? for this first part, hopefully everyone got this as your first one. Now we can move the double bond over. I could also have it as a primary position. All right? So the double bond essentially is sort of acting as what our nucleophile used to do, right? Our nucleophile would help stabilize the carbocation. Our electron-rich double bond can still help stabilize something that's electron poor. So what I want you to try to do is now let's put this together with what we've already learned about SN1. So underneath that, I have a reaction with the two products already. I will tell you right now, if it's a secondary halide, that is allylic, what mechanism are we now expecting this to go via? SN1 or SN2? Secondary, that's allylic. We're treating that like a tertiary. If it's a tertiary halide, you'd always expect SN1. First arrow should be kicking out that iodine. Then show me the arrows that can give both of those products. So that's fine. Just make sure that you'd be adding, like you'd still need to draw the nucleophile adding, and then if it's neutral, deprotonation. Well, be careful when you draw the arrows, right? Because like this would be really resonance, and then you could go that out. Does that make sense? Yeah. This looks good. Just be careful about if there's no really draw the resonance and then you draw this around the board. Like this, it's like you can't move this out and that move there. Does that make sense? Because you're showing.
Oh yeah.
Because you're showing that. You can do it, but you can't do it in the same
This is
picture.
leading there.
Yeah. Yeah, that's what I was saying earlier. Just be careful about how you're showing it in two pictures, but you need to show that adding and then not leaving there. That's the jump.
What's the right way to write this?
Well, just be, you don't want to have.
Would you do like an arrow going from like one structure and then put like
It would be
negative
resonance.
of
Yeah,
each three?
it would be resonance from that spot, and then.
Could you just show on the board what you're saying?
Yeah.
Okay, cool.
That's good.
What would the carbocation be?
Which carbon you point to? The one at the double bond?
Yeah.
That moves over. Does that carbon have four bonds? So where is it? What carbon doesn't have four bonds? Right. It feels a little weird because it's a primary, right? But that's the one that's missing the bond. Okay. So I wanted you to to start with this example because it really involves a lot of the chemistry you've already learned. The only thing is now it's a twist, right? I'm saying you're still going to have your nucleophile. And so what I would say is this is how I would start it, by just generating my two carbocations. If the arrows you want to add to that, if you want to add the arrows in there, that's fine. But then just be careful about, if you're drawing the arrows, I would redraw this just to show that you don't want to show resonance arrows and then show nucleophilic arrows on the same picture. Okay? So I would show my two carbocations, and then I would add each nucleophile individually to that. Okay? So I have my nucleophile come, right? Even though that H is leaving, you need to show me that, right? We can see from the products, I don't want any H's just disappearing. So in this case, it's methanol was my nucleophile. You need to deprotonate, and then I also have it here. I don't even have the rest of it finished, because I'm sure you can figure out how to go from there. You'd eventually just remove your H. Okay? So same thing, I would say, really, is the same. Now you're just saying, wait, can I move the carbocation before I have my addition? Sort of like rearrangements, right? You said, oh, if I made a secondary, do I have a tertiary next door? Is this in a allylic position? Then I have a second carbocation generated. And so we won't talk about it today, but from a synthesis perspective, having two products isn't going to be great. So there is a way we can say, let's direct to which one of these products. And so that's the concept of kinetic versus thermodynamic control, and we'll talk about that on Tuesday. I have some nomenclature here for you, but for time reasons, I'll skip it. You can practice those if you want. Just remembering that everything's the same from alkene, except now that we have two, so you have a diene, right? Dibromo, dienes, it's just like a normal substituent. Okay, so I'll let you practice those, and I'll post those this afternoon. So the first reaction we're going to learn is very specific for allylic positions. And so what we've seen before when we had an alkene and a halogen, we actually saw them adding to the double. If we do this at low concentrations, we actually can get an allylic bromination, meaning the double bond will stay there and will add a bromine to the allylic position. And just to keep things straight, around with, well, how do I know if it's X2? How do I know if it's going to add to the double bond or the allylic position? So this new reagent, what this is abbreviated as NBS. Okay? And so this is a way for us to have a very tiny amount of bromine that won't add to the double bond. It will add to the allylic position. Now notice the example I picked here. Just like with our carbocation, if I have two spots where my radical could go, I'm going to have two products. But if I don't have anything else on the ring, whether it goes to this allylic position or this allylic position, we make the same product. Okay? If I have two different allylic groups, I will have two different products. All right? But NBS, you are thinking allylic bromination. All right? Don't think, oh, they're not going to, I'm pretty sure they're just not going to show you that structure. They're just going to abbreviate. That's what I saw in the synthesis practice questions for the rest of 118B. So remember, NBS, you're thinking allylic bromination, and why this is, once this is here, all the chemistry you learned about bromines applies. So I can do an E2 reaction. I could add this double bond here. From there, I could add anything I want to that double bond. I could change I could add epoxides. I could add nucleophiles, other nucleophiles. Okay. So how this actually happens is that free radical bromine using the HV light, right? That actual, what it does is that NBS splits the radical from the nitrogen and the bromine. We create our Br radical here, pushing the radical onto that carbon. At this point, I can have two different radical species, right? I can have the radical on the position where my hydrogen was taken, and I also, through delocalization, can place my radical on my other carbon. And so, in that example, still, my R groups are the same. I'm not seeing much of a difference. Here we have a difference. So NBS is going to add a radical to your allylic position, meaning I'll see this as my first structure with my radical right on that carbon. First CH2 group outside. I think these aren't written great. Notice there's 5 CH2s, now there's only 4. So that first CH2 group has the radical on it, or really it's a CH group, right? Your hydrogen was taken. And so I can add a bromine to that position, or I can move the double bond over, bring the same arrows that we drew in the first exercise of today, right? My fishhook arrows. To place my bromine on this primary carbon. And so I'll actually see a mixture of both of these products. And even so, when we move that double bond over, right, notice here I'm saying mixture of cis and trans, or E and Z. So radical chemistry is happening really fast. Whatever allows this to add the quickest, it's going to do, even though we know trans would be greater than cis. So, what does this mean for you, for reactions for synthesis? Right? If I give you this, I'll go back in a second, but if you have that, I want you to go ahead and think about what would NBS do, and then as well, how can you use NBS, and I gave it as an arrow, in the bottom synthesis part. Okay? What I drew for you was 1 octane, if you couldn't tell. That way, if you wanted to go bond line, it's there for you already. Still won't be that spot. Right. It will be somewhere else. Yeah, so you moved the double bond out of the hydrogen position. So we can't start this way. So the flame can be that way, but then the double bond will go away. But there is one more I can make. That's good. That's good. Remember how this starts is it needs an allylic hydrogen. So is there a hydrogen at that point? So the radical is going where you're drawing those 2 H's. Once you're there, add the bromine, show the allylic one. So there is 2 products for this first one. Once you've generated the radical, you know how we can move the double bond to help it. Great. That's it now. This is all about allylic position. So not going to add to. Yes, that would be one. Is there another one? you moved the double bond already? Draw the first one. Yes, that'd be great. Moving the radical over there.
No.
You're moving it, and you're moving it the right way, but remember the three radicals, so the arrows are wrong. Yeah.
Oh, and it's from the radical?
Yeah. Yep. Good.
Working on this.
Yeah, that's
That's
no.
right.
Yeah.
Okay.
That's good. I wouldn't do it twice though.
Got it.
Great. That's good. That's the radical.
Yeah.
Okay. So remember, once the radical is help. One. Okay, because I'll leave it alone. Okay, I'll give you another minute. So again, 2 products. I will tell you that for the bottom one, if you don't remember the 118, how we mean on there, very similar to what we did today, right? The NBS with HV gives us an allylic bromine. The Br2 with HV gives us a bromine on an alkene. So that's structure. So I want to highlight this again just to make sure everyone's on the same page. This is looking for an allylic hydrogen to get started. So why I picked this example is there's only one allylic hydrogen, right? This top position does not have an H. And that's why I blocked it. I put 2 methyls there to make sure I didn't add the bromine on that spot, right? If I had 1 methyl group there, I now have 2 allylic hydrogens. And I could add the bromine in both spots. Okay? But with the double protection, I cannot. I'll only add it initially in 1 spot. So I will create my radical being at this position. Once the radical's there, a bromine will add there. And I think everyone pretty much got that first product. Remember, this is just like an anion, a carbocation, and you can turn over your paper because this is what we started with, right? I told you there was a radical here, and we moved it to the other position using the double bond. So that means if the radical's on this spot, the double bond can move over, making the radical on the other position. So your 2 products look like this. Your first bromine here, your double bond has moved, and now the radical is located at this carbon, so the bromine can add there. And for this chapter, you need to get comfortable saying that if this was a carbocation, just like the SN1 we practiced with, everyone saw that there were 2 different carbocations you could make there. This one is doing the exact same thing, just with radicals. Any questions on that? That's like sort of the big new reagent for this chapter. Okay? First step would be adding the HV bromine. Once I get my bromine on there, I can add a double bond via an elimination reaction. Now, once I've added a double bond to it, I can use NBS to add a bromine. In this case, both of these positions are the same. So that's why I will only add once, right? That NBS has just that 1 bromine on there. So we can't add twice. From there, I can do everything we talked about, but if I want it, I can now make sure this eliminates. And if I don't even think you need the bulky base here, but you don't want it to be a nucleophile. That's why I'd say it's a little bit safer to do. But now I've added a second double bond there. And so what we will talk about on Tuesday is, now if we have 2 double bonds, I can add acid to 1 and create an allylic carbocation that allows delocalization from the other double bond. All right? And that's what we'll pick up on Tuesday. Thank you for coming even now. I hope it's a little bit of a break. I'll be in on Monday in the morning and the afternoon.